Hello and welcome to the Fully Charged Show podcast. I'm Helen Czerski. This week we are going to be flying high all the way out into space. We know that our energy on Earth is limited, but the sun, sitting there at the middle of the solar system, emits energy in all directions, and Earth only crosses a tiny fraction of its total energy output. So there's lots of other energy out there which is carrying on out into the universe. Could we make use of some of the rest? Well, this week we're going to be talking about space-based solar power, which the acronym for that is SBSP, which is a terrible acronym, far too hard to say. But could we collect energy up there out in space and transport it down to Earth? It sounds like something that's out of a sci-fi book from the 1960s, but you know, we live in quite a sci-fi world. Could you make this work in practice? This week's guest is Ian Cash, who's the chief engineer of IECL, and his company have got a design for a system that could apparently do this, and there's also a general government feasibility study that's going on at the moment, so perhaps this is closer than we all think. Now, I have to confess right up front that I'm a skeptic about this. I can see so many obstacles to making this work, and they're not really the engineering obstacles. The thing that I think we need to think about here is, who owns the orbits of satellites? Who decides who gets to use them? The radio frequencies you need to communicate in space and to send energy around using this system. Like, everyone is going to fight, even more than they do now, over radio frequencies in the future. There's the regulations, like who makes the laws about all of this? And does society want something up in space sending energy down to Earth? So I think all of those are massive obstacles that are far harder than the technical ones. But, Ian thinks this could be real. So could he change my mind? Well, here's the interview so you can judge for yourself.
My Energy is putting the I back into British innovation. My Energy is putting the I back into inventing the future. My Energy is putting the I back into inspiring a nation. Recharging the world with green, smart energy. Charge your EV with your PV and more. Visit myenergy.com and help to spark the green revolution. My Energy, driving the charge to a greener future.
Ian, thank you for joining us today. Let's get straight into the big idea that you're here to talk about, because I think it's something that will not be familiar to most people. So tell us what this is all about.
Okay, space-based solar power. So everyone is now familiar with terrestrial solar power, but it does have some issues, particularly when it comes to the day-night cycle and intermittency due to weather. With space-based solar power, the idea is that you have a solar power satellite in orbit, which can basically see the sun 24 hours a day, 365 days a year, with only very tiny outages, just a few days each year. And that can convert solar energy into microwave energy and beam it down to Earth 24 hours a day, no matter what the weather is doing. And so it can deliver baseload power, which is the golden thing that we need in the UK and elsewhere around the world. So
let's just dig into because this is one of those things that it sounds like something from a cartoon, from like a sort of cartoon magazine for kids from the 1960s almost. That this is just as simple as just a thing in the sky and it just happens. So without getting into too much detail, just what has to go in the sky and where does it go, and what has to be on the ground, and what connects those two things?
Right. So the satellite which needs to go into orbit, it's very much like any communication satellite. It's doing the same things. So a communication satellite in geostationary orbit that has large solar panels, converts solar energy into electricity, and it also has microwave transmitters for beaming communications, whether it's your Sky TV or telephone calls or internet. So we've been beaming microwaves at Earth from satellites for a long time. The difference with space solar power is the scale. These satellites have to be very, very big. On the ground, much as for terrestrial solar, we have large solar farms. You would have something similar, but it would actually be bigger still, and it's called a rectifying antenna, or rectenna. And that converts microwave energy back to electricity into a form which can then be fed into the grid. And it can do so very efficiently as well, sometimes about 90% efficiency.
So before we get on to sort of because obviously, all I've got in my head is a whole load of very practical questions about how this may work. But before we get there, like why we've got solar panels on the ground. They're quite nice. Yes. We can get to them with a screwdriver and a soldering iron when they go wrong. Why is it worth even thinking about putting something, many thousands of kilometres away in space when you could just have one on the ground?
Well, let's look at the UK. So at the moment, the UK has an average base load power. This is power we need 24 hours a day of about 20 gigawatts on average. So over a year, that's an average base load power of 20 gigawatt years. Now, a fossil power plant, such as a coal-fired power plant, typical size of that might be 2 gigawatts. So that's the sort of thing we'd want to replace. And if you look at the UK has also just given the go-ahead for a very large solar farm down in Kent called Cleve Hill. And this solar farm also incorporates a very large, I believe it's the world's largest lithium ion battery as well. And this gives the chance to reduce or eliminate the daily intermittency of renewables, particularly solar power. And this has a nameplate capacity of about 1/6 that of a 2 gigawatt fossil power plant. Its nameplate capacity is about 350 megawatts. So this is one of my bugbears that whenever you hear about terrestrial renewables, they only figure that's usually quoted is its nameplate capacity. And this is very misleading.
So just tell us what a nameplate capacity is, because I think that's probably not very familiar to most people.
Well, it's a very useful figure and basically tells you what the peak power this facility can produce. And that will be something like in the middle of summer on a very clear day around noon when the sun's as high in the sky as it can be, what's the maximum power this can produce. So that's very useful for the engineers who are designing the facility and the infrastructure which goes around it. It's not very useful for the consumers or for the population that wants to decide, is this a good plan or not? I happen to think this is a very good plan, the Cleve Hill facility. So when you look at the intermittency, if you look at other large terrestrial solar farms in the UK, there's a thing called the capacity factor, and that's about 11%. So that suddenly when you look at the average power that this facility will produce around the year, if it followed the same format as other large terrestrial solar farms, you're only going to get about 40 megawatts. So 40 megawatt years instead of 350 megawatt years. Now, Cleve Hill is unusual as well because they've actually packed in as many photovoltaic panels as they possibly could. And that's not typical. Previously, when panels have been more expensive, you tend to try and get the most power out of as few panels as possible to maximize the bang for the buck. With Cleve Hill, what they've looked at is trying to maximize, they've got an area for this facility and they're trying to maximize the amount of year-round energy that it can produce. So I think they're going to do better than this 11% utilization factor. I think that they might well get up to about 65 megawatt years from it. But the important thing is that this is what you get on average. But what you need to consider is what's the worst case in winter? And if you look at the sun hours that the UK gets, which is defined as 1 kilowatt of sunlight landing in 1 horizontal square meter of land in the UK. On average, the UK, we get about 4.4 sun hours. And in winter, it can drop to about 1/4 of that, about 1.1 sun hours.
But you can use that for quite a lot of things, So
yes,
we all know
absolutely.
Robert's got solar panels on his house, and that keeps him going, even in the British weather. It's not useless energy here.
Not at all, no. And I'm not trying to suggest it is. What I'm trying to do is compare this very large solar farm. How many of those would you need to actually replace a 2 gigawatt fossil power plant, a coal-fired power plant, for example? So in winter, you're going to expect, on an average winter, about 20 megawatt years from it. And on a bad winter, it might be as low as 15 or 16. So if you take somewhere in between that, say, allowing for some poor winters, you're going to get about 18 megawatt years. That would mean, and the storage that goes along with it, the 700 megawatt hour battery, if you can use about 60% of that capacity, that would actually be good for 18 megawatts average on a day for 23 hours, which fits in with the 1.1 sun hours that the UK gets in the middle of winter, on a poor winter. So Cleve Hill is a very good model for baseload power, but you would need 110 of them to compete with a 2 gigawatt fossil power plant. And where a fossil power plant might cost you £500 million, this would cost you something in the region of £30 billion.
But there's plenty of other sources of power, right? I mean, you would use wind power during the winter. Solar panels, well, solar is not the only option.
We've got, in the UK, if you look at how much fossil fuel we actually consume, so about 1/5 of that is for electricity production. But if you look at the whole lot, it's about 200 gigawatt years. So that's 100 of such a fossil power plant, and another 110 times that if you want to do it with terrestrial solar. If you look at the wind, the capacity of wind is only about 1% that of solar. So if you maximised out the amount of wind, the UK is blessed because you get the best wind energy is coastal.
How are you doing that calculation? I'm gonna play devil's advocate here, because obviously all wind energy comes from the sun. Ultimately, exactly. When you're talking about from the...
So it's a secondary effect of sun. But these figures, in fact, I can give you the quote on that. So Chris Goodall, who wrote, he has a website, carboncommentary.com, and he's written a book called The Switch. So he has this. So the total, the average sunlight power hitting the whole of the Earth's surface is a little less than 90,000 terawatts on average. If you look for the wind potential, it's about 900 terawatts. That's 1% of the capacity of solar. If you look at biomass, that's about 90 terawatts. So that's 1,000th the capacity of solar. The total wave potential is about 7 terawatts. So that's 0.01% of solar.
But this isn't a reasonable comparison, though, is it? Because solar energy runs the Earth system, right? It goes into the oceans, it creates the weather. It's not all available power. So let's maybe get back to the sort of the critical thing about the technology that they're talking about, the space-based solar power. So let's have some numbers on this. So one of these systems, however big it is, you were talking about a 2 gigawatt power plant. What could one of these space-based systems produce?
Right. Well, actually, from geostationary orbit, you can't really choose any particular power you want. Once you've chosen the frequency you're going to use, and you want to keep to this safe peak intensity on the ground, because we don't want to break any regulations, then for 2.45 gigahertz, that will basically give you about 2 gigawatts baseload power delivered into the grid. That's 24/7. If you look at the size of the rectenna and the average electrical power over the size of the rectenna, you're going to get around about 6 times greater energy density than the average power that the terrestrial solar will give you.
So what would one of these systems cost compared with a power, equivalent power generation on the ground?
Well, at the moment, it would cost something less than a nuclear power station. But that's not the whole story, because just as for terrestrial solar on the ground, which you can only use for 11% of the time on average, if you look at the cost of the energy, the levelized cost of energy coming from space, it's actually economically viable right now. And again, I have some figures for that. Hinkley Point nuclear power station, that's costing a 22 billion project, and the cost of energy from that has been priced at about £90 per megawatt hour. For space-based solar power, near term, it would actually come in at about £20 per megawatt hour, so a lot cheaper than nuclear power. even though the cost for one solar power satellite and one antenna would be about £6 billion. So yes, it would cost less than nuclear, but the cost of the energy it produces would be a lot less than nuclear.
But we know that nuclear is expensive energy, right? Possibly of all the energy types we use, nuclear is the most expensive option by a long way. So how does it compare with other energy types?
No, because if you compare for the Cleve Hill project, which can produce baseload power, but when you look at the equivalent for replacing a 2 gigawatt fossil power station, you'd need 110 such facilities, and that would cost you more than £30 billion. That's actually more expensive than nuclear.
But you wouldn't replace. You wouldn't do that, right? You'd get your energy in other ways.
Well, we need storage. So if we look for this worst case example, which is a December day when you're not getting much solar power, we've had 2-week dry spells. So we need storage. We know we need storage. And if we built out solar sufficient and used lithium-ion batteries for your daily storage, then we'd need about 5 times the world's known reserves of lithium to achieve that, and would need a land area about 1/4 the area of the current used agricultural land in the UK to achieve that.
But there are other ways to store power that aren't batteries. I mean, no one's talking about batteries for everything.
Yeah, so it's lithium batteries would not be suitable for seasonal storage. For that, you'd need to use chemical storage. And a very good chemical to use would be ammonia, because ammonia is basically hydrogen and nitrogen. And when you burn it, you basically release the nitrogen and produce water from the oxygen in the air. So it has zero global warming potential. It's very safe with the ozone layer. And it's a usable fuel. We already use a lot of it now as fertilizer, but it can be burnt in internal combustion engines if that's something you want to do.
It comes with a few NOx problems, though. Nitrous oxide isn't that great to have knocking around? Oh,
so much better would be to use a direct fuel cell, which takes in ammonia and then just releases the N2 without the NOx. But if you look at the round trip efficiency of storing power chemically as ammonia, then you've got about 40% round trip efficiency. So all this excess solar power you get in the summer, a lot of that excess is lost in the round trip storage efficiency, turning it into chemical fuels. And again, going back to this 2 gigawatt fossil plant we're trying to replace, a good way to visualize how much ammonia you'd actually need to store is to think of one of the very large cooling towers. So for every 2 gigawatts of baseload power you want to produce, and you're offsetting the excess solar power you get in the summer to supply what you need in the winter, you would need about 1.5 million cubic meters of ammonia. And that's about 7 times the size, the volume of one of these cooling towers that you'd see with a fossil
But there are
plant.
there's pumped water storage, and, there are flywheels, and there are other ways to store energy.
Well, let's say pumped hydro. You may be familiar with the Electric Mountain. I think Robert did a show from there. If you look at that and the other known reserves which could be turned into hydro storage, pumped hydro storage, we've got something like 50 gigawatt hours of known reserves. That's with the terrain that the UK has been given, including Scotland and elsewhere. So that would be good for about 1 hour's, is it 1 hour or 1 day's storage at a 2 gigawatt plant. So we can't use that for seasonal storage either. It's good for evening out. It's 1 hour storage. Yeah, that's all we can get with all the known reserves of pumped hydro. So we actually have very few options for storage, particularly seasonal storage.
So the point you're making is that because large-scale storage is difficult, it's better to have a non-seasonal source like space-based solar power because you don't have the storage problem.
So with space-based solar power, the only time when it's predicted that you would lose that power is during the spring and autumn equinox time, when the satellite would actually pass through Earth's shadow. And the longest time it would spend in Earth's shadow is about 70 minutes. On average, it's about 40 minutes over a few days. And that's basically all the storage you would then need to do. or you could use an adjacent satellite which isn't currently in Earth's shadow to redirect power to the antennas. So you could have 24/7.
Well, let's get back to some of the practicalities of how this would work, because I think in a way, all of this does come down to practicalities. Like, there's all these big ideas, but actually there are a lot of practical problems. So I'm just going to run past you some of the practical things that occurred to me off the top of my head, really, which is, first of all, presumably in order to generate this amount of power in space, you're going to need to launch a lot of stuff, and you're going to need to launch it all the way to a geosynchronous orbit. So you're going to need very light, flat solar panels. And once they get there, you can't maintain them. So run us through that. How do you fix, first of all, the launch problem? It's getting cheaper. There's private vehicles. It's still not cheap. But then once you get all this stuff out there, you can't fix it.
Right, so you want to design your satellite for a 30-year lifetime, or 20 or 30-year lifetime, and that's something which we achieve with geosynchronous satellites now. They do have this multi-decade lifetime. So you would aim for graceful degradation. You wouldn't try and service these with astronauts, replacing panels. But the launch issue, yes, the cost of space solar power is all down to the launch cost currently. So you may be aware that in the shuttle era, the cost of launching anything to space, whether it was food or dirt or water, was about £20,000 per kilogram. So it would cost you about the same to lift gold bullion as it does to lift water. And that's come down to under £2,000 per kilogram. And we have that today. And right now, using the Falcon Heavy, if we wanted to use that, then we would that would cost about £4.2 billion per gigawatt and produce energy at about £26 per megawatt hour. So actually, that even today, it's economically viable right now. But the other question that people ask is that, well, what about all the fuel you're using, all the propellant you're burning, all the carbon dioxide you're going to be putting into the air? Now, this is where I'd probably move away from the work that SpaceX is doing with Falcon Heavy and now the new Starship design. It's very important as a fully reusable Starship, but it is methane-based, so liquid methane, liquid oxygen-based. So the UK has done work. A company called Reaction Engines has produced designs for an engine called Sabre, which is an air-breathing rocket engine. And that runs on liquid hydrogen fuel. And most of the time it takes the oxygen from the atmosphere. But
it has a second stage, right, which doesn't. And Sabre's not a heavy lifting. It's not for heavy lifting, right? It's a two-stage system.
No, but if you look at just in terms of the amount of fuel needed, the amount of liquid hydrogen needed, well, we know that we can produce green hydrogen by electrolyzing seawater. And if you look at how long would it take to actually pay back that energy cost of the propellant needed to take it all the way, not just to low Earth orbit, but all the way into geosynchronous orbit, which needs a lot more propellant, including this upper stage, which you just mentioned, which is a reusable upper stage. It's not thrown away. It's returned back to the cargo hold. So it would actually take about 23 days to pay back that energy cost, which is nothing over the lifetime of the satellite.
So we should probably just explain a little bit about Reaction Engines. So this is a company based in Oxford which does basically uses hydrogen as fuel, and their two-stage system is the idea that you use one system of propelling yourself to get yourself up to reasonably high, and then you basically switch to a separate system to take you even higher. And they've been working on this for years, actually, and it's got a huge amount of potential. It's not as far as I know, they're not anywhere near launching any of these things yet.
Well, Reaction Engines, the clue's in the name. They're an engine designer. So the air-breathing space plane design, that's something they did as a reference model to prove that there was a case for using their engine. But yes, we need the funding to get a fully reusable spaceplane with airline-like operations so that we can have this rapid turnaround and ultra-low cost.
So let's go back to the price and sorry to interrupt. Let's go back to the price and the how big? So what's the weight that you need to get into orbit for one of these solar based, solar energy collecting satellites, what does it weigh?
In
How
the
much do you have to put
1970
up there?
In the 1970s, with the efficiency of solar panels and things, it was about 10,000 tons, metric tons per gigawatt. With more recent advances, other concepts around there, they've got that down to about 5,000 tons per gigawatt. The Cassiopeia design is a novel UK design. I'm the named inventor on that. It has no moving parts. So you need a sun-facing part and an Earth-facing part, which beams the microwaves to Earth. And between the two, you need to have a rotating joint as the satellite goes round in its orbit.
So let's get a picture in our heads here. So, if you could describe the shape of it and why part of it needs to rotate, because that's quite an important question.
Right. So the shape of it, if you're familiar with DNA, a double helix, this is like a short section of 180-degree twist double helix. And the thing about that, if you project a shadow from this helix, it doesn't matter how you rotate it, the area of that shadow stays the same. So this concept is called Cassiopeia, which stands for constant aperture, constant projected area, solid state, there's no moving parts, integrated orbital phased array, which is the microwave transmitter. So what's different about this is that the satellite always faces the sun. And that allows you to use the most efficient photovoltaics available, which are high concentration photovoltaics. In the labs now, they're achieving about 47% efficiency. You can buy them as commercial items achieving about 40% efficiency. That's much better than the best silicon panels you can use on the Earth, which are only, say, 23% efficiency.
So where are the solar panels? So we've got this DNA, so we've got this kind of spiral going round. Where are the solar panels on the spiral?
So the rungs of the DNA, they are very thin layers with photovoltaics on both sides. And between the layers, it's basically open to space, but that's where the microwave antenna sit. So you need a couple of mirrors, top and bottom, so as this faces the sun, it then redirects the sunlight down to the north-south axis, down onto the top layers of all these layers in the helix, and also up from the southern side, again on the other side of all these layers. So what that means is the photovoltaics and the microwave emitters are within millimeters of each other. The whole functionality of the satellite can almost be captured in about a 25 millimeter cube. Everything you need that the satellite does can be captured in such a small, very highly modular volume.
Sorry, so that's tell us what the 25 millimeter cube is?
So that's, if you look at the microwave elements, and the high concentration photovoltaics, which would rather being very large panels, these panels would actually only be about 1 millimeter square, and concentrate sunlight hitting them will be concentrated about 500 or 600 times. So even though these would be very expensive materials, you need 500 or 600 times less of them because we are directly facing the sun.
So let me make sure I've got this in my head. So there's a big mirror at either end.
Yes.
That is, so we've got a kind of stick, I guess, a very long. How long is it from one end to the other?
For the best design, which concentrates 4 suns with 4 mirrors, that's going to be about 5 or 6 kilometers in length.
Okay, so it's a big thing.
Oh yes, absolutely.
And
massive,
then there's a mirror at either end, and the mirrors stay there, sort of 45 degrees, so they're direct sunlight from the sun down parallel to the stick, and then all
and it's collimated sunlight.
The actual solar panel bits are in between the mirrors, if you like, so they're catching the light that's going sideways.
That's right. Yeah. So
okay.
The mirrors are only just sized sufficiently to capture all the energy which will be beamed down as solar power onto the photovoltaics.
Okay.
So the question you asked to begin with was about the mass of this thing. So I mentioned historically in the 1970s, it's about 10,000 tons per gigawatt. More recently, that's been got down to 5,000 tons per gigawatt. Now, my own analysis, Fraser Nash and the government are doing their due diligence on this as well, but I've got this down to about 1,000 tons per gigawatt. So a 2 gigawatt, and this is the power delivered to the grid, will mass about 2,000 tons.
Okay, so if you can get all of this stuff up into space, let's start off from the outside there and work our way in. So there's this big rotating thing that can collect solar energy using these mirrors.
When you say rotating, I disagree. This is permanently facing the sun. It only appears to be rotating from the Earth's perspective.
Right.
But this is where the novelty comes in, because usually phased arrays, if you look at a textbook on microwave phased arrays, you'll find that the steering angle is limited to about plus or minus 45 degrees typically.
So we should just clarify here that what you're talking about now is you need to get the beam pointing down to Earth, and what the process of beam steering, so it's not just like you have a laser pointer when you generate microwaves. You need to do some clever stuff with a very large antenna to generate a narrow beam. So it's not like you have a narrow transmitter and a narrow beam. You need this big thing.
And this is where the pilot beam...
And this is beam forming, what with beam steering and beam forming we're talking about.
And that relies heavily on the pilot beam, which is being emitted from the antenna. But the Cassiopeia design can steer this microwave beam, so it can form a very tight beam, which is still going to be about 5 kilometers across by the time it reaches the Earth, and steer it 360 degrees around the satellite while it stays pointing absolutely straight at the sun. And it can also steer it north and south as well to reach the likes of the UK, which is at a relatively high latitude.
So just before we leave the satellite itself, how about, cosmic radiation, solar radiation? This is outside the Van Allen belts, the space debris, well, there's not so much out there. Low Earth orbit, there's a lot. But so how about the radiation damage? Because things do get degraded in space, and this is quite a delicate thing. I mean, to make it that light, this must be really quite fragile, actually, thin and fragile, if it was on Earth. So what do you do about the radiation damage that stuff gets in space?
Well, I'd refer back to geosynchronous satellites, which have been sitting in the same relatively high radiation environment. It's not as bad as the Van Allen belts in geosynchronous orbit. But the photovoltaics themselves, they're absolutely exposed to this radiation environment, and they achieve a 20 or 30-year lifetime. So typically they would degrade, and you would see about 80% of their performance after that lifetime.
So even with these...
That has actually been factored in.
Very efficient ones that you're talking, the 47% efficiency, there's also, they can last that. Has anyone done those tests?
Yes, absolutely. It's the same technology which is used on the ISS now. With their rollout solar arrays.
Okay, so, and just be clear again, so geosynchronous orbit, just for those people who don't think in orbits all the time, basically things are generally put in one of two orbits. There's low Earth orbit, which kind of whizzes around once every 90 minutes. That's where it's not quite where the International Space Station is, but near there. So all those things that, are spinning around the Earth lots of times a day, where the satellites, that kind of thing, they're very close to the Earth in low Earth orbit. And the problem with them is that they move relative to the Earth, they're moving all the time. And then as we go out, you can find an orbit which rotates, where an orbiting object basically matches the speed of Earth's rotation. So a satellite stays above a fixed point on Earth. And there's two kind of classes of satellites. And the geostationary orbit, that's the big one that's further out.
And it's a lot further out as well. So the ISS, the altitude of the ISS is about 400 kilometers. The altitude of a geosynchronous satellite, a COM satellite, which is in geostationary or geosynchronous orbit now, that's 36,000 kilometers. So yes, it's a very long way. But half the cost of getting payloads into orbit is to low Earth orbit, and the other half is to shift it into a geosynchronous orbit. But there's other orbits which can be used as well. There's highly elliptical orbits, which can be quite beneficial for space-based solar power, but you need the right concept. And a lot of the concepts which are around today use a thing called gravity gradient stabilization, where basically you divide the mass of this satellite into two big pieces, and it's a bit like a pendulum, but it tends to orientate itself so it faces the Earth. But because it's got such a high moment of inertia, they won't work in highly elliptical orbits where when it's close to the Earth at perigee, it's moving incredibly fast, very high angular velocity, and when it's out at apogee, it's got a much lower angular velocity. Because Cassiopeia always faces the sun, it doesn't have this problem, so it's perfectly suitable for working in these other useful orbits, which could allow for lower scale implementation, less than 2 gigawatts at much lower cost.
So let's start moving in from, there's this big structure in space which is expensive to put there. You put it there and then you sort of leave it and it does its thing, and then there's this beam. You need to get this energy that it's collecting down to Earth, and so you've got a microwave antenna. So there's something on board the satellite that takes the voltage that is generated by the photovoltaic cells, converts that into microwave energy. And then if you've got a 5 kilometer long satellite, do you need the full length of that to form the antenna?
No, the helix itself, if we're looking at the Optimum model for geosynchronous orbit, it's about 1.7 kilometers diameter and also 1.7 kilometers tall. So the rest of that is for the 2 pairs of mirrors needed top and bottom to do some pre-concentration of the sunlight to give you about 4 suns hitting the structure.
So then, okay, so we've got this bit, and it's got an antenna on board, and then now we get to this issue of getting that energy down to Earth. And first of all, so microwaves are, there's lots of communications happen in the microwave wavelength. So I can put my physicist hat on here. What, like, those frequencies? So for those, for the audience who don't think in the frequencies of light all the time, the microwave region is really useful for lots and lots and lots of things. And it's a spectrum. It's a part of the frequency spectrum that is much fought over because everyone wants to use it for their thing. And of course, the wonderful thing about like old-fashioned radio dials, if you tune a radio dial, you can just hear your frequency. And the question is that, sometimes you get interference between 2 stations. If anyone is old enough to remember those old radios, I am. So there's this question of, frequencies start to interfere, and very clever electronics can narrow down the band, and everyone's kind of squeezed down exactly which frequencies they're using. And there's a system for deciding who uses which frequencies. And a lot of microwave frequencies are used for weather satellites, communications, sensing. So how do you find space in this crowded radio frequency spectrum to be beaming energy around?
It is definitely a challenge. That's one of the biggest regulatory issues that space-based solar power will have, is how to use part of the spectrum. The most likely solution is to use one of the ISM bands, which is industrial, scientific and medical use bands. And you'll be very familiar with these because one is the same frequency as used by the microwave oven in your kitchen, 2.45 gigahertz. And the other is about 5.8, which is around 5 gigahertz Wi-Fi, but actually just outside that. And interference, generally, you're talking about interference from other communications equipment, which has a wide bandwidth. So,
well, I was actually more talking about you interfering with them.
Oh, exactly, yes. But because it's power beaming, we are of incredibly narrow band. So we don't take up much bandwidth, and any spillover into sidebands will be at a much lower level. And the other thing is that if you look at, do you worry about anything interfering with your 27 megahertz CB radio?
I don't use a CB radio, but
27 megahertz.
It's not critical. I'm not relying on it for my power supply.
Yeah, but you see that frequencies are moving ever higher. So if you look at 5G services now and 6G, which is being talked about, they're moving to 25 gigahertz. Space-based solar power can't use anything above 10 gigahertz anyway, because it's opaque. You get so much lost through the atmosphere. Where both 2.45 and 5.8, the losses even through severe storms and thick cloud is only about 2%. So that's why you've got this 24/7 power delivery. So yes,
so how about the satellites? So you said, you're beaming these microwaves. We haven't got to the atmosphere yet, but the satellites that are orbiting in low Earth orbit, presumably they're going to pass through this beam. How does it affect them?
It's about a quarter the strength of sunlight. So it's not actually a high intensity beam. It's just a large area.
But does it interfere with their antenna and their comms?
Typically, satellites, if you look at the Starlink satellites, they're using Ka and Ku bands, which are around 25 gigahertz, above and below 25 gigahertz region. 24 gigahertz is another ISM band, which is strongly absorbed by the atmosphere. So no satellites use that. So that's well away from the 2.45 or the 5.8 gigahertz that space-based solar power is most likely to use. So no, you wouldn't expect interference with that.
So I think there's a really interesting thing here, which is coming up more and more, which is that space, before we even get down to Earth, but we'll get there, not yet, that space is really crowded, that, the actual, so the CubeSats, the Starlink thing that Elon Musk is basically put up there, and it keeps multiplying the number of satellites. I think it was five. I think there's 5,000 up there now, and there's another 20,000 due. And this terrifies quite a lot of Earth scientists, because they get in the way of Earth observation, and people worry about collisions, because if that collides with the other one, then you've got loads of bits everywhere, and they'll collide with other things. And so there's this kind of debate, I guess, is the present way to put it, going on between the space you need for the satellites to orbit in without bashing into each other, because they have very limited, they can steer a little bit, but you've got to keep track of them, and also the frequencies they use to communicate, because that is incredibly crowded. And so one of the things I think is very interesting is the regulation of who gets to do what. Elon Musk seems to think he isn't really subject to the rules. He just sort of does things and no one can stop him. But there is this question about who gets to decide, right? There's people are already arguing over frequencies. They're already arguing over the space. You turn up with some great big solar panel in space that wants to sort of go through all of this. How does this work with who gets to say? Because space law does exist. I have met space lawyers, but who gets to say, what if the world doesn't want a microwave beam pointed at it? How does this get split up between countries, right? What if one country wants one and another one doesn't want you to have a microwave beam? How does all of that stuff work?
Well, if we're talking about geostationary orbit, then there's a lot of competition for orbital slots, because we have all these communication satellites there already. So that's a big issue, that will we be able to get the slots we need in geostationary orbit? But there's a very good solution to that. That's just one orbital plane, which happens to coincide with Earth's equator. But there's another orbital plane called the Geosynchronous Laplace plane, which is what's called a frozen orbit. So in some ways, it's very good that you need very little station-keeping propellant. So it's more efficient to operate in this orbit. You don't need to be having... Well, it's 50 meters per second per year of delta V.
You should probably just explain what Laplace, what these Lagrange points are, and all that kind of thing.
Okay, the geosynchronous Laplace plane, basically, it's, as I've said, it's a frozen orbit. So it's a natural orbit formed by the inclination of the Earth and the ecliptic plane, which is the plane that planets travel around the Sun. And it's part way between the equatorial plane and the ecliptic plane, but it was devised by Laplace, and it is just this highly stable orbit. But it's not used by geostationary satellites, because it means that all the Sky TV antennas on your houses would then have to steer to follow the satellites as they travel in a figure-of-8 pattern. With space-based solar power, we've got to have this microwave steering anyway, and that's no issue. So that would be a very good orbit to use if we're going for geostationary.
Okay, so let's move on in. So now our microwave beam it's got through whatever is in low Earth orbit, and it's arrived at the atmosphere. So how what are the losses? I guess there are always losses somewhere. So what are the losses as this stuff passes through the atmosphere?
So if you look at 99% of weather, so that includes severe rainstorms and very thick cloud, the losses you'd expect at 2.45 gigahertz would be about 2%. So 98% of the microwave beam travels straight through unimpeded. If you want to know the other losses, so the rectenna, converting this microwave to electricity, that was demonstrated in the 1970s at over 90% efficiency. And the first stage of converting the electricity at the satellite into microwaves, that we can do that at about 85% efficiency. So when you add all this efficiency chain together, it answers one of the first questions about how inefficient it must be to send this power from 36,000 kilometers. Don't we know about the inverse square law and things like that? But well, actually, no, the efficiency is about 60% or more. that we can achieve on beaming the microwaves, converting electricity to microwaves, beaming across 36,000 kilometers and receiving it at the rectenna and feeding it into the grid. That's about over 60% efficiency.
Okay, so let's move on to what's actually at the ground. So how big is this target and where is it? What's it look like?
Well, it would have to be at least 5 kilometers across, and at the moment that's difficult to find such a contiguous area of land. So for the UK, the assumption that Fraser-Nash are using at the moment is that it would be in shallow coastal waters, such as the Thames Estuary or around the Isle of Man. And
I can think of a few issues with putting it in the Thames Estuary, but carry on. It's very busy around there.
Yes, but if you're comparing to, say, the Cleve Hill solar farm again, where they've packed in their photovoltaics, very little sunlight is actually going to get through to the ground. With a rectenna at 2.45 gigahertz, the wavelength is about 12 centimeters, and you could basically make the rectenna out of a mesh of about 3 centimeter mesh. And that's going to let sunlight through, it's going to let precipitation through. Potentially, you could erect this over farmland.
So is this a sort of giant net? Is that the thing you're describing? A net that is 5 kilometers across?
That's one way it could be implemented. Obviously, it wouldn't have to be one single net, but you would have to basically reserve a large area, and you wouldn't want roads and things going through it unless you're using a secondary net as shielding.
And what about around it? Because presumably, however good your steering is, you're going to want some space on either side of your 5 kilometers to, there's got to be some wiggle room in there. How much space do you need at the sides that isn't actually your collecting array, just for safety?
Right. Well, you're the first one to mention the airy disk. So this is the central spot region, which is what would be interesting in converting. And the diameter of the rectenna, we normally consider capturing this airy disk, which is about 84% of the total power in the beam. And by the time you get to that first minima, then it's already at regulatory safe levels for continuous exposure by the general population.
What about the next maxima, the next little bump in the...
Oh, yeah,
so we should explain to people who for whom an airy disk is a new thing. They're quite cool. But basically it means that whenever you are focusing light of any kind in this kind of way, you get a central spot, and then around it there's a ring where there's not very much, and then there's another ring where you get a bit more, and another ring, and there's kind of stripes going out that go down in power. So the central spot is the bit where they're collecting arrays. But so sorry, Ian, carry on with these. You get that minima, and then you get another little maximum. So how far out do you need to go before?
If it was perfectly focused, then the number of minima and maximums actually extends out to infinity. But it's a matter of diminishing returns. So the rectenna would have to be so much bigger if you wanted to exceed, if you wanted to capture 90% or 95% of the energy. But basically, outside of the airy disk, because we've already set the peak intensity at the very center is about 230 watts per square meter, a quarter of the strength of sunlight. By the time you reach outside the area of the airy disk, which is about 5 kilometers diameter, then it's already at regulatory safe levels for general exposure by non-qualified population.
Okay, so all right, so then how about, let's come back to the question. So then it goes into the grid or wherever it goes, and things, off you go. You've got your baseload power if that's what you're after. So one of the things I think that's really interesting about this kind of technology is that there's this tendency in the world, and Elon Musk is actually we'll call him a good example of this, is that there's a tendency for engineers to come along and go, I know what the world wants. The world wants what I've just invented. And then the world goes, actually, we didn't really want that. We don't like the idea of this. Can you please go away? and there's this terrible thing where, it's not terrible at all. It's very human that really what society needs is not defined only by technical numbers, right? It's defined by what's acceptable, what's ethical, what's possible without causing a war, which might be relevant in this case. Humans are terribly bad at sharing when it comes to, that's why space law is so interesting, because We're not even very good at working out what to do about the ocean. It's a lawless place. We're not very good about working out what to do about Antarctica, even in spite of the Antarctic Treaty. It's creaking around the edges because it turns out there might be valuable things and everyone's very keen on that. And it seems every time humans have a space where there aren't any existing rules, the Arctic Ocean is becoming another one. Humans are not good at sharing. They are very good at scrapping and being territorial. And there's things people aren't comfortable with. So what happens? What's the feeling? I don't know if this probably isn't included in the government's technical consultation, but what is the response to this? Like, do people want this? If we could have a wind farm, or we could have a satellite far out in space that might go wrong without us being able to fix it at a moment's notice that we're relying on, do we want that instead of a wind farm? Like, what's the actual response from people who are not engineers?
We want all of the above. We need to have a diversity of energy sources. So wind power is very good. Terrestrial solar power is very good, particularly when it's backed up by lithium-ion storage to cover the daily day-night cycles. But the problem is that we've got 200 gigawatt years of oil, coal and gas consumption in the UK, which we've definitely had for 2018 and 2019. And it's how can we replace that? If it's going to take 110 Cleve Hill solar farms, which is one of the largest solar farms ever planned for the UK and possibly the world's largest battery, and if that's going to cost £30 billion, because that project is £450 million, so you need 110 of them, when you could do space solar power for a lot less money, you'd use 1/6 of the land area, it automatically gives you baseload power, so you don't need the storage, other than for 70 minutes of outages. It's an advantage, but it's only going to be one part of the mix. I'm a proponent of nuclear power. I think it's got a very safe record, but it's also very expensive. Fusion power, if that comes along, then yes, we need that. That would be a great source of carbon-free power. But again, the fuel cost isn't going to be free there. There's still issues with how we're going to generate the helium, so the tritium and deuterium. Deuterium's easy. The tritium we need to generate because it doesn't last. There's some big science issues which still need solving for fusion power. Where space-based solar power, we've been beaming microwaves to Earth from satellites since the late 60s, so we know exactly how to do it. It's not a science problem to solve. It's a massive engineering challenge. No doubt about it. We've never built anything so large in space before. But
how about societal acceptance? Because, I mean, you mentioned nuclear power, and actually nuclear power stations, again, whatever you think about nuclear, you can get to them with a spanner. So why not build? So I'm kind of interested that you say you're a proponent of nuclear power, because this, is not that much cheaper, but it's a lot harder to maintain and look after. But
the fuel is free. So because it's such a highly modular design for the Cassiopeia concept, you can expect to lose modules over its lifetime, but you're going to see graceful degradation, and that's been factored in so that the power delivered to the grid, that's its average power over its lifetime, not the early years or the latter years.
And how about societal acceptance? Because, it's very easy to understand, to explain to the public what a wind turbine is. And what's your response when you present this idea to, people who are not engineers, and that's the critical point? What do they think of it? Do they want it?
I think there's a lot of misinformation going around to the layperson who perhaps doesn't understand what microwave energy is. They think that, could it cause cancer, for example? But it's non-ionizing radiation, so it cannot cause DNA damage, for example. So there's a lot of uproar about 5G services, which are also microwaves at higher frequencies than this would use. I think it comes down to convenience as well. Would people reject their microwave oven in the household because it uses microwaves? I think in the early days when microwave ovens were first introduced, there was some wariness about it because you couldn't see what was heating the food. And there was a worry about, what's it going to be doing if you're standing too close to it? So I think all these things, yes, there will be some public acceptance and some public rejection. But by initially beaming to offshore locations, and you're not going to have the same visual impact from a rectenna, which is going to be fairly close to the ground, rather than, for example, wind farms, which some people object to. I don't personally have any problem with wind energy. There shouldn't be that level of rejection. But at the end of the day, how are we going to replace the fossil power which we're still burning today? It's a big issue, and can we do it economically? And if we try and do it just with terrestrial wind and solar, we're going to be using up a lot of the UK sources. If we were trying to do it just with solar, then we'd probably be using about a quarter of the agricultural land. And
I don't think anyone's talking about doing it just with solar. Let's talk about timescales then, because so if, there's this very preliminary government review going on at the moment, this feasibility study, if they conclude that it's worth someone putting some money into this, how long would it take to solve the technical problems you're talking about?
Well, a lot of the issues are being worked on right now. So, for example, Cassiopeia itself is a new issue. None in the textbooks say you can steer a microwave beam through 360 degrees, not with a non-redundant design. You can do it with multiple antennas. So I'm lucky to have in my basement here at home my own electronics and RF laboratory. And I'm busy putting together a prototype which will actually prove that concept. It has already been proved in concept form independently by the University of Strathclyde, for example. But if we pull out all the stops, if the government gives the go-ahead, then we could expect first satellite on orbit in the early 2030s. And I think it's only worth doing this if it's actually delivering some useful power. So it's unlikely that this will just use a standard low Earth orbit, because I think that could be detrimental. Because unless the satellite is big enough to deliver useful power and stay over any particular region for more than 15 minutes at a time, I think that would be a source of non-acceptance. So I think a good place to actually deliver first power may actually be Antarctica, where the cost of shipping, it's like diesel fuel, AN8 fuel to the South Pole. It's horrendous cost. But by mounting a few rectenna panels in Antarctica, that could actually give green power where the cost of energy is already very expensive. And that would be a good demonstration of a prototype system.
Well, I was going to ask about that, because if you're generating energy in space, why not use it in space? There's all sorts of people are starting to, satellites themselves, they do have a power. Yes. One of the problems with them is that they have very limited power supplies in some cases, so why not, if you're going to generate energy in space, why not use it on the moon or for low Earth orbit satellites? Oh, yes, why use it on Earth?
Well, you mentioned the moon. I've actually written a paper about exactly that, because that's one of our next targets, is putting men and women back on the moon. And we're aiming for the polar regions, because that's where we found that there's traces of water. With water, you can electrolyze it to create air to breathe, the oxygen. You've got water to drink, and also the hydrogen and oxygen makes rocket propellant. So it would be a good self-sustaining colony. Very few carbon and nitrogen deposits there, so you'd have to ship those to a lunar base. But there's a big problem with solar power on the lunar surface, and that's the duration of the lunar night, which lasts 14 days. And the amount of storage you would need, particularly if you're using something like lithium-ion batteries, it's even more horrendous than what you'd need for large scale on the surface of the Earth. So there you would definitely be looking at electrolyzing water to store liquid hydrogen as your chemical fuel source. So I've actually compared what it would take to supply a small colony on the moon compared with surface photovoltaics compared with a solar power satellite. And my conclusion was that it was preferential. And it's just the opposite to the Earth, where building things and maintaining things on the Earth is relatively cheap compared to trying to maintain things on orbit. With putting things on the moon, that's an extra step of actually soft landing equipment on the moon. By leaving it in orbit, and the only thing you need on the moon is rectenna panels, then that actually reduces the amount of mass you need to ship to the moon.
So there's something else. I'm just thinking about, the world is full at the moment of people who are coming up with ideas for generating energy, and because we need other ways of generating energy, as we've said. And I imagine there are rooms full of people, engineers, politicians thinking about things. And I'm just wondering what kind of reaction you get when you walk into those rooms, because I think like many things, the biggest problem with this is the regulation. Other people want those frequencies. Other people want that space in the sky. It's not a question of can you do it, because you could. It's a question of, do we want to do it? And does that, can you prioritize that over all the other priorities people have for weather satellites and, whatever else communication satellites in low Earth orbit are doing, and in geosynchronous orbit. So when you walk into these rooms full of engineers and people thinking about energy and you start talking about this, what kind of reaction do you get from them?
Generally, the kind of rooms I've been walking into has been fairly positive. And I think there's an understanding now that we've got a limited time available to try and reduce the amount of carbon dioxide we're pumping into the atmosphere. So it's all of the above. Any new power sources, we haven't got the luxury of rejecting a new power source on principle without at least exploring it thoroughly. So we need to have at least a solar power satellite on orbit where it can be properly assessed. And if it's decided that, hey, fusion energy has already arrived and that's meeting all our needs at the price point we want, even then, I'd say we still need this diversity of power. So that includes wind power, wave power, terrestrial photovoltaics, nuclear fusion, nuclear fission, all of the above. But we need to so drastically reduce the amount of fossil power. And sometimes when these new renewable energy projects only state the nameplate capacity, I think that's doing a disservice. They're not stating in real terms how many of these you would actually need to replace a fossil power plant. And that's what we need to be doing over the longer term to reduce the amount of carbon we're pumping into the atmosphere.
And who else? The UK government's looking into this at the moment. I think, is it the US and China? Are they the other two? Who is looking into this seriously?
US, China, Japan, South Korea, ESA.
And are these feasibility studies, or are these actually starting on the engineering? Because the feasibility study is the first, until you've got past that state. There's this history with these technologies. Oh, we'll have a look, and then maybe it's not right now, and then we'll have another look. Have any of them got past the stage of, oh, we'll have another look at it?
Yes, I've actually met quite a number of the people actually working on these designs. So they're a fairly advanced level. So, for example, the Chinese, they have two different concepts, one called SPS Omega and the other MR SPS, which is multi-rotary joint SPS. And I've seen the technical details for these, and they're at a fair level. I've actually visited the university in Xidian, where I saw some of the prototypes for the SPS Omega design, which was very interesting to be able to see that.
So just finally, because we've done a lot of talking, we should probably finish soonish. If you had to put a bet, like an honest bet, not your bet as the, someone with skin in this game. If you had to put a bet on this being an industry, not necessarily launched, but an industry which is seriously doing things with a reasonable number of people trying to solve engineering problems by 2030, what percentages would you put on that without your try and be as neutral as you can here, because obviously all inventors think that their thing is the thing that's going to solve the world's problems. But if you were being honest, what would you pick?
So I think if we're talking about China, I'd say it's inevitable. They were very likely to be the first to launch a solar power satellite to orbit, because they really are taking this seriously. They actually do want to tackle climate change. For the UK, I think I would say it's probably 50-50, and it won't be the technical feasibility, which has already been very favourable from the preliminary results that I've seen from this Fraser-Nash study. And it probably won't be the economics as well, because we're talking about a concept now which is 10 times less massive than that was looked at in the 70s, and that directly relates to the cost. And the cost of launch has also come down about 100 times now. So it's not going to be the technical or economic viability. It's going to be the other regulatory or gut feeling response which might just stop it. And it could actually be some of the green movement thinking that this might actually detract from terrestrial photovoltaics and terrestrial wind and wave power, things like that. But I think we need a diversity of energy sources, and I think the more the merrier. And if we're investing billions of pounds into fusion research, where we're still looking at materials science, among other issues, and plasma physics, then I think this is worth some small but ongoing level of investment from the UK government.
Brilliant. Well, that is a great place to finish. Thank you very much, Ewan. It's been a pleasure to talk to you.
Thank you. Likewise.
I hope you found that interesting. I certainly learned a lot. I have to say, I am still a skeptic. I'm very open to being proven wrong, but I can see so many obstacles here. It's just a rat's nest of complications in terms of actually getting people to agree on this and how it should work. What really did excite me, though, is the potential for collecting power to use in space. It seems that it's far more sensible to collect energy in space to use in space than it is to send it down here. So, I don't know, let's look out for the results of the government's feasibility study, and maybe it will all happen. Maybe it'll be here certainly before I expect. You can make up your own mind about what you're expecting to happen. But if you've liked this and you'd like to support us, please subscribe to Fully Charged on Patreon. Subscribe to the Fully Charged podcast and look at the website fullycharged.show. None of these things are easy to say, but anyway, fullycharged.show. And if you have been, thank you for listening.